Hey everybody, let's take a minute to talk about force and its relationship to potential energy. Up to this point, we've been analyzing systems almost exclusively using energy. We can learn a lot from analyzing systems this way, but we can't learn everything. One of the things that we're interested in physics is known as force. A force is exactly what it sounds like. It's just a push or a pull on an object. For example, if I apply a force to this chair, it moves, as we would expect. It turns out there is a direct relationship between force and potential energy. To see how this works, let's analyze a system we've never seen before. We're going to be looking at a system that involves gravitational potential energy, except it's not going to be gravitational potential energy as we're used to seeing it. Instead of thinking about the gravitational potential energy of an object near the Earth's surface, we're going to think about the gravitational potential energy between two very large objects far apart. For example, the Earth and the Moon. The graph of potential energy for this case looks like this. In this graph, r is the distance between the objects. For example, the distance between the center of the Earth and the center of the Moon. PE is, of course, the potential energy. In this case, it's gravitational potential energy, but the analysis we're about to do works just as well with any kind of potential energy that we're interested in. I'm not going to go into why the potential energy graph is shaped this way. This graph technically says that the potential energy of the objects becomes infinite as they approach each other. Of course, the Moon is quite some distance from the Earth, so we don't really need to consider this part of the graph. Let's see if we can figure out from the graph what the force in this case is. Let's think for a minute about what we expect to happen for the Earth-Moon case. We don't expect you to know how these kinds of situations work. I'm just using it as an example. The strength of gravity between two objects depends on two things. First, it depends on the mass of the individual objects. Secondly, it depends on how far apart those objects are. The farther apart the objects are, the smaller the gravitational force between them. The second fact that we need to know is that gravity is always attractive. Gravity is never going to push one object away from the other. They're always going to be pulled together. Let's see if we can relate these facts to this graph. Let's ask ourselves, is there something on this graph that decreases as the objects get farther apart? In other words, is there something about this graph that gets smaller as r gets larger? There are two things that I see. The first is that as r gets larger, the potential energy gets closer and closer to zero. The second thing is that as r gets larger, the slope of this graph gets smaller. One of these turns out to not matter, just as when we did potential energy with an object near the Earth. What we call potential energy zero does not actually matter in this case. By convention, we take potential energy to be zero when objects are very, very far apart. But there's nothing particularly special about this choice except that it makes the math easy to work with. The other thing that we identified as getting smaller as these objects got farther apart is the slope of this graph. It turns out that that's the quantity that matters when we're thinking about force. The strength of a force is related to the slope of the associated potential energy graph. But it's not exactly the slope. Let's think about that here. The slope of this graph is always positive. However, we know that gravity is attractive. This means that gravity wants to make r smaller by bringing the two objects together. So the slope of this graph is positive, but the force itself is negative. It wants to make r smaller. It turns out that force is the negative slope of potential energy. There's a way we can write this in calculus. It looks like this. This just says that force is equal to the negative derivative of potential energy with respect to position. Now note, I used R in this case to denote position. There's nothing special about using X to label position. In this graph, I used R to label position. Whatever variable you use, it doesn't matter. Let's think briefly about what this means for the system. As we said, the slope of the graph everywhere is positive, meaning if we take the derivative of this function, we're going to get a positive number. But if we then add a negative sign, this number becomes negative, meaning the force is attractive as we expected. The second thing to note about the slope is that the closer the objects get together, the steeper it gets. That means when we take this derivative, we're going to get a larger number here than we would over here. This means that the force between the objects will be greater when they're close together than they are when they're far apart, which is exactly what we expect for gravity. We're going to see several different potential energy graphs in this course, so I want to give you a way to think about this that's a little more visual and easy to see. If you want to figure out the direction of force, imagine placing a little marble on the potential energy graph. If we place this marble here and let it go, it would roll this way. If we put the marble down here and let it go, it would roll to the left, just as the force between the objects is also to the left, towards decreasing distance. This works no matter how complex your potential energy graph looks like. One of the graphs we're going to see later in this course is called the Lennard-Jones potential. I'm not going to go into the details of it now, but let's just take a brief moment to see how this visual analogy works in that case. The Lennard-Jones potential looks like this. As before, let's imagine placing a little marble, say right here. If we release this marble, it's going to roll down into this well. But then it's going to start rolling up the other side. However, there's no way that it'll get all the way out. At some point, it will turn around and start rolling back the other way. We're going to use this potential energy graph when we're talking about bonds between atoms, but we'll save that for a later DL.